So welcome back to our course on Introduction to General Relativity for physics students. This time we're beginning the second lecture with a discussion of the equivalence principle, gravity, and apparent forces. Okay, so let's go to it. Everyone knows the story of Newton, where he was observing an apple on a tree, and all of a sudden the stem of the apple broke and it fell to the earth. Sounds like a trivial thing, of course, and why would it inspire anyone? Well, it inspired Newton because in those days gravity was not particularly understood. Okay, it was past the era of Kepler, so it was understood that there was gravity, and somehow or other it guided the planets on orbits around the sun. But besides that, it wasn't really understood. I mean, gravity as a force that occurred between separate masses wasn't a concept out there. There were planets and they were special. There was the stars and they were special. That was the cosmos. It was Newton who came along and said, no, there are forces. This is a particular kind of force, and it's universal. It acts between any two masses. Why is that a revolutionary idea? Well, here, if I have a mass over here and a mass over here, I don't notice any force between them. Okay? So it's a remarkable thing to think that the force is universal. But Newton saw the asymmetry here of a tiny little apple feeling the gravity of the earth. He saw that the apple fell to the earth. So little objects experience gravity, not just planets. It's not just a property of the cosmos, it's a property of everything. It's universal. Okay? So the idea was then that masses attract one another according to a law, Newton's law of gravity, and here it's written down that the force between the two masses, m1 and m2, falls like the square of the distance between them, along the line between them, with a universal constant called Newton's gravitational constant, which is taken from experiment, taken from actually fitting the orbits of the planets around the sun. Okay, now how did he know it was F goes like 1 over r squared? Did he guess it? Well, you know full well, because maybe you read the historical lecture number 2, I think it is, okay, which pulls out of the Principia the derivation of Newton's law of gravity from Kepler's laws. You have the 3 laws of Kepler, and you have the concept of a force, and then Kepler's law tells you, in no uncertain terms, that the force has to fall off as 1 upon r squared. Occurs between the bodies, along the radial line between them, is proportional to the product of the masses of the two bodies, the star and the earth, for example, okay, or the sun and Jupiter, for example, okay. So that's what he's learned. That's what he wrote down. Take a look at that supplementary historical lecture if you've never gone through the exercise of deriving the law of gravity from Kepler's laws. I know most of the textbooks on mechanics go the other way around. Okay, they derive Kepler's laws from Newton's theory of gravity. Boy, is that misleading, right? That's not how history was. Newton didn't guess the 1 upon r squared law. He got it from Kepler's the analysis that Kepler did, where Kepler came up with the 3 laws, and the 3 laws imply 1 upon r squared within the context of Newtonian concepts. Okay. There were other physicists at the time that were fiddling around with the same ideas, Hooke, of course, and they were also getting close to 1 upon r squared, and in some of their writings they also wrote it down. But Newton's our man. He's the one that made the big difference. Okay, then, so Newton would write this down, and then he would solve for the orbits and the motion of particles in gravitational fields. The force is mass times acceleration, so we'd write that down here. Here I'm imagining the Earth going around the sun. So here's Earth, mass of the Earth, position of the Earth. Here's mass of the Earth, mass of the sun. And of course we notice that the thing that everyone noticed, of course, was that the force is proportional to the mass. That's Newton's law. And from Newton's second law, the force is proportional to mass times acceleration. So the mass of the Earth disappears. Okay. So the mass of the Earth disappears. So if you replace Earth on its orbit by a feather, the feather would take the same path. Okay, there's more universalities here than Newton imagined, and it will be Einstein will say that that in fact every mass takes a path. Okay, so that path must be a property of geometry, not a property of forces, because of its extra universality, and that's part of the subject of general relativity that we'll be getting to. So here I say force goes like mass. In this particular case, mass goes like inertia, and so all masses acquire the same acceleration and travel the same paths. I remind you that the history of Kepler's laws and the fact that Galileo established, okay, that the force of gravity was proportional to the inertial mass, and the acceleration of a body dropped off the Leaning Tower of Pisa was independent of its mass. So that leads us to think, well, do I know other kinds of forces which have that quality? That's certainly not the case in electrodynamics. That's not the case for spring forces. Okay, there, the acceleration is inversely proportional to the mass of what's being accelerated, of course. Okay, but there are some forces that are independent of mass, and they're apparent forces or virtual forces, like the force of Coriolis or centrifugal force. Or in just day-to-day situations, let's say you're stopped you're driving your Tesla, and you're stopped at a red light, and you want to accelerate off of that red light, okay, and so you hit the gas pedal, which then it gives acceleration, okay, and it gives that acceleration to all the masses in that car. That acceleration is then common. In Coriolis or centrifugal forces, okay, those are forces that are independent of the mass of the object. If I take a mass and stick it on a rope and swing the rope around my head, then that mass suffers centrifugal acceleration, and that centrifugal acceleration is given to me by the geometry of a point going around on a circle at constant angular velocity. So any mass experiences the same acceleration. That's centripetal acceleration, and Coriolis, the same idea. In that particular case, the particle is moving let's say along the radius of a rotating turntable, and it experiences a force to the left or to the right. Okay, and it's the Coriolis force. Okay, so here I just remind you of that. I'll consider a turntable with a rate of rotation omega, and so here I have a turntable parameterized by x and y, and I have a point here, r, and it has an angle theta, and the whole gadget is rotating. Okay. Okay, so then how do I write down the equation of motion for it? Well, first I might take my Cartesian coordinates and write them in terms of plane polar coordinates that are better equipped for rotating reference frames and problems of this sort. So x is then equal to r cosine theta plus omega t. Okay, so the variable theta plus omega t indicating convenience of a point that might be rotating. If, for example, I hold theta fixed, then x depends on the angle omega t in a sinusoidal fashion, and it rotates around the axis, which might be the z-axis coming out of the paper. And then y is just the other projection of this point r. The projection onto the x-axis, the projection onto the y-axis, and r is rotating with an angular frequency omega, then there are its coordinates. Okay, so let's imagine then that this is a mass point, and in addition to rotating, it might experience some external forces as well. It might be a charged particle, for example, and going to experience a radial and an angular force in addition to rotating. So I have to write my equation of motion in a non-inertial reference frame, in a rotating reference frame. In other words, I have to just implement this transformation, okay, and then get my equation of motion not for x and t in a Cartesian coordinate system, but for r and theta along the rotating turntable. It's an exercise then in just coordinate transformation, okay, and so I do that, and it's done in the textbook. Okay, I don't want to do it here; it's a lot of arithmetic. Oh, we're going to learn a very easy way to do this problem. Okay, later we'll use as soon as we get used to Christoffel symbols, we'll use them and we'll write this down in one step. Okay, I guarantee it. I'm not slipping anything under the rug here. I'm not doing a pulling out of the air a hard problem and you know and such. We're going to do it right. But let's do it later, because I like rather doing it in a slick way rather than just slogging through a lot of algebra. Okay, that's right. So anyway, so we get the when we do the exercise, we'll get the acceleration in the radial direction, okay, and the equation will have the acceleration, the explicit acceleration, and then it'll have an extra term here, which goes like r angular velocity squared. That's centripetal acceleration, okay? And it just comes from the change of coordinate system. It's familiar to us. And then if we looked at the angular motion of the of the particle, okay, in this direction as it's rotating, we'll see another effect. We'll see the Coriolis effect. We'll see that the second derivative of theta has a contribution which goes proportional to the rate at which the particle is moving in the radial direction times the rate at which the turntable is rotating. Okay, so I have omega, which is an external parameter. My system is rotating, and then I have the theta dt. That indicates to me the rate at which the angle is changing as the particle is moving on the turntable. So I have, that's my left-hand side of the F equals ma. Okay, this is the ma side, and I've taken the mass and thrown it onto the other side of the equation, because all of these terms are independent of mass. So I have to throw it on the other side of the equation. And so for the radial equation, then I get the component of the external force in the radial direction divided by mass, and similarly in the theta direction. Right? So you see the ingredients here. When I simply write the acceleration, okay, in the non-inertial reference frame, I get a term I might consider familiar, an explicit second derivative, but then in addition I'll get the virtual or apparent forces coming from the rotating reference system, and I recognize here centripetal and Coriolis forces. Okay. What's going to be interesting is that when I come to look at the equation of motion of particles in curved space-time, I'm going to find the same structure. A second derivative of a position, and then effects of the curvature in addition, equaling some external force. This is where gravity will be, the apparent forces, and the explicit forces might be electrodynamics, or some other external force which does not affect the geometry like gravity does. Gravity affects the geometry, and so it comes into the left-hand side of the equation, but electrodynamics being explicit and on the right-hand side of the equation. So we're going to be looking for effects like that. Okay. So in general relativity, I'll give you a precursor here, that energy momentum will produce curved space-time. Gravity, so we're going to curve space-time, so gravity is going to determine the paths of particles through the curved space-time. We won't have an explicit force for gravity, we'll have curved space-time instead, and we'll find gravity as an apparent force now. Now, we're going to spend a good deal of the time on the interface, okay, between Newtonian physics and Einsteinian physics. And there we'll see the correspondence between virtual or apparent forces and gravitational forces and the curvature of space-time. So we'll be quite concrete about it. This might be a little bit vague. I understand that at this point, okay, but we'll we'll be doing better later. Okay, we want to just get the intuitions down a bit, discuss them a bit, and then move on. Okay, and here's another example. For example, the problem of a mass in a uniform gravitational field minus g. Here we are. Here's Earth. Here's a mass that's being pulled down by gravity from Newton's perspective. From Einstein's perspective, this problem is the same as the problem of the motion in a rocket with acceleration plus g. Okay, so here I am with my mass again. I have no Earth, okay, but I'm viewing the motion of the mass from the perspective of an accelerating frame, which is accelerating upward, right? So the environment of the mass is gravity pulling down, or rocket accelerating up, and these problems are, according to the equivalence principle, exactly the same. Okay, that's a hypothesis of general relativity, and we'll want to pursue that hypothesis and see how it works. We want to understand the equivalence principle, that I can replace problems of mechanics in gravitational fields with problems in accelerated reference frames. Okay, so here I have a rocket ship accelerating in an inertial frame. I know in the inertial frame the laws of mechanics, that's special relativity. Okay, and the mass here is just being viewed from the perspective of the accelerating rocket going up. Okay, and that problem is supposed to have the same physics as the problem of the mass outside the Earth. We'll want to also discuss the limitations of this picture. Okay, well, one of the things you might notice right off the bat is that, of course, that the gravitational field outside the Earth is not uniform exactly, right? We approximate it by saying that gravity points down, and since Earth is very large on the scale of people, that's a good approximation. On the right-hand side, we really have a problem with linear gravity, where acceleration going up. There's no other directional dependence in it than that. Here we have gravity. So we'll look at the differences here and be rather precise about it. The idea is going to be that for small enough regions of space-time, okay, I can replace this problem with this problem. If I look at large regions of space-time, then of course the curvature of the Earth, the curvature, the R dependence, the angular dependence of the gravitational potential plays a role here, and so it doesn't map to a problem given by the equivalence principle. It maps to another problem which we're going to try to understand, and in that problem we're going to find curvature, and we're going to find the Einstein equations of the field here. So let's keep pursuing these ideas. That's the equivalence principle, and the equivalence principle stated in its strongest form is that it applies to any physical process. So I have a mechanics problem like that, okay, and it'll satisfy the equivalence principle that the problem in a gravitational field is equivalent to the problem in the accelerating rocket, okay. But in the strongest form, okay, since mechanics is the basis of physics, it's supposed to apply to any physical process. Well, one of the most surprising applications might be that I can replace that mass m by a light ray. Okay, there's another physical process. It's supposed to apply there. So I'll put a light ray in the previous example. So here it is. Here's a light ray, and it's traveling transverse to a gravitational field which pulls down. Okay, but that's supposed to be equivalent, okay, to the light ray traveling in a reference frame, okay, which is accelerating up. Okay, which accelerates like in our picture. Gravity was pulling us down. We made it equivalent to the problem where the rocket ship is accelerating up, so that in both cases the mass was experiencing the same phenomena. So shooting a light ray here on the surface of the Earth. Okay, I don't know what happens. So I make the mapping by the equivalence principle to the problem of the light ray, okay, propagating in a reference frame that's accelerating upward. Well, relative to that reference frame, what happens? Light falls. light falls. Mapping back to the original problem of light outside of a planet, I see that the mass of the planet is attracting light. Okay, so the attraction of gravity, using Newton terminology, is really universal for a light ray as well as a point particle. And I can write down how it works here. I can see that I can label the path of light as y as a function of x. So I see that the second derivative, the second derivative of this path, it isn't quite curvature, but it's related to curvature, okay, is approximately equal to, well, upstairs I have y, that's the height of it. Downstairs I have dx squared. This is light, okay, so I can approximate dx squared by saying that, well, that the light is traveling for to lowest order. The good approximation is x equals ct, so it looks like that, okay, and so I can see here, therefore, that I get dy squared dt squared, okay, divided by c squared. But dy squared dt, that's the acceleration of the light ray in a frame which is accelerating up, okay, so the light ray is experiencing that acceleration, okay, and so relative to the coordinate system that's accelerating up, it's accelerating down with an acceleration minus g divided by c squared, okay. And so I have an estimate then. This is approximate, of course, because I'm replacing x by ct for a path that has slight curvature in it. So I'm not getting it precisely right. I could do it better, but it's the concept that matters here. The concept that light falls in gravity. It's attracted. You would say, going back to the original description, it's attracted to the mass, and that leads to gravitational lensing. Okay, here's a big mass. It pulls. I can do the equivalence principle mapping for this fellow in this particular region and see that light bends down, and similarly the light ray over here bends up, and that the big mass tends to lens the light that comes across that mass. Well-known phenomena in astrophysics. Okay, so it's used as a measuring device for finding masses. Uses measuring devices for exploring far away light sources as well, and it's called gravitational lensing. Okay. Okay. So again, as we see here, the equivalence principle can only be applied locally over regions where G is approximately constant. That was clear in the example of lensing. I was thinking of the equivalence principle. Locally, how it was pulling down, how the gravitational field was pulling down on the light ray. Okay, so let's take a look at another problem, okay, which involves apparent forces, and that's a rotating relativistic frame. Instead of getting halfway through it and then having to quit, why don't we just pick it up here and take a look at rotating relativistic reference frames next time.